So welcome everyone, and thank you so much for joining us for our third annual Diversity, Equity, Inclusion, and Justice in Environmental Data Science seminar series. And today we have the pleasure of welcoming Grace Wu, our third and final speaker in the seminar series. Now, if you missed our previous two speakers, I would encourage you to go over to our YouTube channel where all of the videos from the seminar series are posted. And I also just wanted to take a moment to thank our organizing committee and all of our speakers for their hard work to make this entire seminar series such a great success. My name is Alex Phillips, and I am the Science Communication and Policy Officer here at NCEAS, which stands for the National Center for Ecological Analysis and Synthesis. At NCEAS, we work to accelerate scientific discoveries that enhance our understanding of the world and benefit people and nature, as well as to transform the scientific culture to be more open, efficient, and collaborative. For more information, please feel free to check out the NCEAS website. And before we begin, I'd ask for you to join us in acknowledging the Chumash peoples, who are the environmental stewards of the land on which NCEAS is located. We pay our respects to the Chumash people and their elders, past, present, and future, who call this place home. We acknowledge that this land on which we live and work are the traditional homelands of Indigenous peoples, including the Chumash people. This land today is the result of the erasures and exclusions of Indigenous peoples. As we come together to bring awareness to issues of equity and justice, we recognize that the Chumash people and so many other Indigenous people are still fighting to dismantle the legacies of settler colonialism in their tribal territories. As we continue to work towards diversity, equity, inclusion, and justice in data science, we strive to prioritize Indigenous data sovereignty and self-determination. Thank you so much. And now I'm going to hand it off to Ingrid Slete, who's going to introduce you to our speaker for today and give you some logistical information about this presentation.
Great, thank you for that introduction, Alex. I'm Ingrid. I am a postdoc here at NCEAS, and I am so excited to welcome today Grace Wu for our DEIJ seminar series. For all of you joining us for this webinar, please submit any questions that you may have during the talk using the Q&A button located at the bottom of your screen. We encourage you to write any questions throughout the presentation, and then we will get to them at the end during a moderated Q&A session. And now I'd like to introduce our speaker today. Grace Wu is an assistant professor in the Environmental Studies program at UC Santa Barbara. Before joining UCSB, Grace was a Smith Conservation Fellow at the Nature Conservancy and here at NCEAS. She was also a UC President's Postdoctoral Fellow at the John Muir Institute for the Environment at UC Davis. She was trained in systems thinking and interdisciplinary approaches in the Energy and Resources Group at UC Berkeley. Grace is interested in the dynamics and drivers of land use change, climate change mitigation, and advancing our ability to plan for sustainable, multi-use landscapes that protect biodiversity and advance climate goals. She uses spatial science approaches to identify and understand the co-benefits and trade-offs between climate solutions and habitat conservation. Her main current research areas are 1, sustainable spatial planning of low carbon energy systems, and 2, designing policy management and technology pathways to sustainable land systems. Grace, we are so excited to hear from you today. I'll now turn it over to you and you can begin your presentation.
Thank you so much, Ingrid, for that introduction and for this wonderful organizing team for this series. I'm super excited to be here today to share some recent work I've done in collaboration with multiple partners on designing net zero pathways for the US that center not just the technology, but also important values, namely conservation and our communities. So before I dive into the details on the conservation community portion, I want to start by addressing a common perception of renewable energy, which is a big centerpiece of our net zero pathways. That perception of renewables taking up a lot of land. So I'm highlighting a couple of sentences in this news article that was released last year, which is one of many types of articles of this nature, highlighting the fact that renewables, specifically solar in this case, occupies a lot of land, about an order of magnitude greater than a natural gas power plant situated just 100 miles away, and that this is one of the biggest barriers to scaling up renewables is its gargantuan scale. And by answering this question of does renewable energy require vast amounts of land, I'm going to both validate what conservationists and communities are afraid of and concerned about with this rollout of renewables, but also vindicate wind and solar, hopefully in that process. So I want to say that more than anything having to do with the size is we're experiencing this fundamental shift in the visibility of energy and where it's located in our landscape. We're moving from a traditional fossil fuel electricity generation system in which where that fuel is being extracted and where that electricity is being generated are found in different places. So we're looking at a highly disaggregated generation landscape where the mining and extraction, for instance, is located in a place like Wyoming. It's then transported in a pipeline that may be above or below ground. And then it's sent to a facility to be processed and stored, and then finally transported to its actual power plant, the natural gas power plant, which we most visibly see because those are the infrastructure projects that are located closest to where people live. Now we're transitioning to this new energy landscape dominated by wind and solar electricity generation, where we've taken this 4-phase fuel cycle and generation cycle that you see with natural gas and condensed it into a single location, where we basically see a vast expanse of windmills across a large wind farm, or a vast expanse of solar panels on a very large solar farm in a very concentrated manner. So this visibility issue and where it occurs suddenly becomes a very different way of interacting with energy in its location. And I want to clarify both now from an empirical and just a numbers basis, and I'm going to move into the nuance of all of this in terms of what it means for people and plants and animals. The first is based on the most recent research published just earlier this year. We can find that the fuel cycle and generation cycle of natural gas generation uses about 200 square meters per unit of electricity generation. Here I'm using gigawatt hours. So the thing to pay attention to here is the smaller the number, the more land efficient this generation technology is. So with natural gas, it's 200. Let's contrast this with solar generation. It's about 300. So it's higher, so it's a little less land efficient. And it is based on this important number, this 30-year lifetime. If we double that lifetime, we suddenly shrink that land use efficiency, or increase that land use efficiency, reduce the amount of land required per unit of generation. And suddenly we are kind of blurring this distinction between which is more land efficient, which is more land sparing. And I want to further emphasize that because we are working with the beauty of a renewable technology, the longer that power plant, that solar power plant is in operation, the more land use efficient that power plant becomes. And so in the case of natural gas and solar, for those to be equivalent in terms of its energy land use density, we would need to occupy that land as a solar farm for 45 years. But the longer that plant is there, that the smaller that number will be that you see. And then one other consideration to add further nuance is that several old wind farms are starting to become quote unquote repowered, meaning that we're replacing the turbines with more efficient ones that in this case for Foot Creek wind farm in Wyoming, they're going to experience a 60% increase in wind generation on the same parcel of land, simply by repowering those sites. So my big takeaway with this is, yes, we're going to require a lot of renewable energy. No, it's not more land use intensive than renewables. The major conclusion for that is really the scale. The scale is what's going to be highest, the most impactful for plants, animals, and people. And by scale, I also, in some ways, want to vindicate wind and solar, because we're asking these new technologies to do much more than fossil fuel has done in the past. We're asking it to expand its reach to other aspects of our lives that natural gas generation has not. So it's going to serve a very large purpose. And as a result, it's going to come up against things that we already use our land for. So the figure on the left is a fun image from Bloomberg that shows us schematically how we use our land in the US. So as you can see, land in the US is very much spoken for. So anywhere we try to integrate the vast amounts of wind, solar, and transmission that we need under these highly decarbonized futures is going to come up against some kind of existing land use conflict. And the figure on the right is a state area equivalent for what we may need by 2050. And it's a little teaser for some of the results that I'll show you over the course of this presentation. So this potential use of additional use of land for energy has been given several names in the literature: energy sprawl, green civil war due to the potential conflicts with conservationists. And I want to caveat the figure on the right with the fact that it's not inclusive of all other types of energy production that will require by mid-century, namely biomass, any potential use of natural gas with carbon capture and storage, hydropower, and again, any types of novel technologies, including bioenergy with CCS. So I want to now dive into the motivation for the work and a little bit of the history in particular, because I think that'll give us a lot more perspective on how things have evolved and actually how the research has evolved alongside the evolution of wind and solar siting. So this is one of the earliest large-scale solar plants in the US. It was developed in 2009, and it actually put renewable energy on a very bad footing with the conservation community. As you can see with this press release from Center for Biological Diversity, it was very much determined to be a poorly sited project. And simply by siting it in the middle of a pristine valley, home to desert tortoise and numerous rare plants, very far from existing transmission infrastructure, and would have to be carrying that electricity quite a distance to people who would actually consume it. So on multiple fronts, it was just put in the wrong place. So this is where it kind of began. We are still experiencing these types of conflicts. So this Yellow Pine Solar project that has been proposed and under development in Nevada is another example of a contentious project. The headline on the left is an indication of that people are still very concerned about siting decisions for large-scale solar projects, that this is an issue that's definitely not going away. But at the same time, developers are, and rightfully developers are highlighting the economic benefits that come with these types of projects. As you can see, 400 million in investments, 23 million in tax revenue, number of jobs that are created as a result. So these are two very conflicting benefits and impacts of a new type of energy infrastructure project. So to kind of round out the history of and how this has evolved, we really started, out with this potential energy sprawl impact on conservation, areas of conservation value, coining it as an environmental paradox or green versus green, these kind of conflicts within the environmental community. And then we've started to venture into conflicts with communities. So more recently, in the last 4 or 5 years, we've started to see a lot more rural community conflicts with siting. And one of the biggest indications of this is wholesale bans on where wind and solar development can occur. So Oregon has restricted all solar development on its farmland. And solar developers are coming up against a lot of resistance because of land use conflicts. So communities are now very much in the throes of these siting conflicts that really started out primarily from an environmental perspective. So my main argument, and actually really the motivation for the work I'll be presenting, is that in order to meet our conservation goals, our climate goals, as well as bring benefits to our communities, we really need to consider the location of these power plants. We need to consider them now more so than ever before in energy planning history. Okay, so with that, I'm going to provide an overview, more of a synthesis of 3 studies that I worked on with the Nature Conservancy, and in addition to 3 other partners in the energy modeling world, Evolved Energy Research, Montara Mountain, and E3. So I'm going to describe each of these in a little more detail. So we started out these projects actually in the 2015, mid-2010 era, really thinking carefully about how do we integrate environmental and conservation considerations into renewable energy planning. And so that inspired a California-centric study. We looked specifically at 100% clean and renewable electricity by mid-century, which is an existing, which is a statute within California. And again, our focus was really on environmental exclusions and environmental impact metrics, because that was really what the biggest siting issues were at that time. The study that actually was just published earlier this year, we expanded the scope to look at net zero economy-wide emissions, and I'll explain the key differences between that and our California study in just a bit. And importantly, we started thinking about the social impact metrics, building that into our modeling framework. And actually, that was also inspired by some of the work that we started, preliminary work we did with California, looking at impacts to housing density and where renewable energy could be located with respect to where people are located. And then finally, we just released a study just last month in the form of an executive summary. We're still prepping the journal papers, in which we did, I think, much better job integrating the social impacts upstream and downstream of a traditional energy modeling approach. And we took a much larger geographic scope, looking at the lower 48 states in the US. So I will mostly in this talk be focusing on the Western and national studies and synthesizing the results of those 2. And that is because of the net zero focus of this particular presentation. I do want to say that we conceived of these studies really in the Trump administration. We were really thinking about state level climate action. And I want to highlight that since we started with California, there's been a cascade of other states that have adopted net zero emissions targets. So this is to see the US as a whole achieve net zero is, it could very well be achievable, as there are already multiple 14 states with these types of mandates. And to add to that, the White House released a long-term strategy for achieving net zero greenhouse gas emissions targets by mid-century. So here I want to emphasize the importance of a net zero versus a 100% clean energy target. And you'll see some of the results comparing these two in the next few slides. But 100% clean electricity basically means we're only looking at the power sector, whereas economy-wide net zero emissions includes everything else in the economy that requires energy and could potentially emit carbon. That includes transportation and the heavy industry, any kind of hydrogen use across those other industries, and carbon sequestration, especially if that means directly capturing that carbon from the atmosphere. So the community, the climate modeling community, has really converged on this need to achieve net zero emissions by 2050 to keep in alignment with a 1.5 degree target. So thus we have deemed this the most ambitious and climate aligned long-term scenario. So we set out to understand several aspects of this transition. Namely, we wanted to examine whether specific types of ecosystem protections and our technology choices affect first, total land and ocean use requirements, our optimal technology investments. And by optimal, I really mean what is this ratio of wind to solar under a particular type of portfolio, under a particular set of constraints, and how much is it going to cost us? I won't get into the details of that here. And then specifically, I know that this audience will be much more interested in those environmental and social impacts due to all of this new development. And again, our scope is net zero emissions targets. Okay, so I want to dwell on this, the methodology for a bit, because this is one of the main, I would say, novel contributions of our work, is to take something that was very historically, very technology focused, very kind of least cost approach to energy planning, and wrapped around it several other important considerations around social and environmental impact factors. So what we did was we gathered a lot of data, and I will refer you to the papers for a list of those specific data sets. And we then aggregated those data and used that to build our quote unquote supply of wind and solar and transmission infrastructure in the US. Here I'm just showing thumbnails of the Western US, but we also did this for the rest of the US. And so we constructed a site suitability map for each of our generation technologies. We also routed specific transmission corridors to ensure that that electricity gets transmitted to the people who will consume them. And then this is where the energy planning framework has always been structured around this kind of what the community calls this capacity expansion model, which is basically an optimization model. And it tells you in a certain year how much of each type of generation technology one should invest in under a least cost framework. So here we use two existing models, Energy Pathways and RIO. One is a demand model, so a forecast of how much electricity we'll need by a certain time. And then RIO tells us how much of wind, solar, natural gas, hydropower, geothermal we'll need in order to meet that demand. So this is what is already existing in energy planning frameworks around the US and globally. So everything else you see is kind of our addition to that. After the portfolios, which are aggregated at a really high at a really coarse spatial resolution. So in the national case, multiple states receive one portfolio. In the Western case, each state has a single portfolio. We take that and we downscale it such that we can actually identify the particular places where we were likely to see wind, solar, and transmission development. And we do that using historic data and statistical approaches. And then finally, and most importantly, we do an impact assessment now with this spatially explicit build out. And this involved overlaying those selected parcels with a lot of environmental and social data to figure out what types of habitat would be converted and the demographics of the host communities. So before I move on, I want to just say, I wanted to talk a little bit about the types of technologies we considered, as I have mostly been describing wind and solar and transmission, but there are many other generation technologies out there that are necessary for us to reach net zero. So the first tier of technologies we represented in high spatial specificity, and namely wind, solar, offshore wind, and transmission. In the subsequent slide, I'll also talk about what we did in Power Place National, which is integrate agrivoltaics, which I'll also define co-location and fixed tilt PV. And then the second tier, which is less spatially specific, but there is some specificity. We modeled the amount of urban infill distributed solar. These are utility scale systems, but located within urban environments. We also considered where biomass would be sourced from. Again, this is kind of spatially coarse, it's at the county level. We also took rooftop solar estimates at the state level. And then everything else is pretty non-spatial, but necessary for us to get to net zero. And so these are baked into the capacity expansion model itself. Okay, so I'll just spend a bit of time talking about some of the land-sparing renewable technologies that we developed for the national study. The first is agrivoltaics. Agrivoltaics is a mashup of agriculture and photovoltaics. And this is a nice schematic that shows how agrivoltaics can achieve an overall higher land use efficiency. So say we only allocated land for just growing crops and another parcel of land for just generating solar electricity, we would have to use twice the amount of land as we would if we combine the two. So we would achieve in this schematic's case almost 190% land use efficiency. So there are multiple co-benefits that come with co-locating agriculture with photovoltaics. Other than just being more land efficient, for certain crops, scientists have found higher yields depending on the climate. And they've also found higher PV performance because of the microclimate benefits, lower water use because of the shading, especially in hot and arid areas. And in terms of social benefits, there's diversified income stream for farmers. So they can still be under production and sell electricity to the grid. And in terms of worker conditions, the shade during midday really provides much healthier work conditions. We also modeled co-location. So in our case, co-location here is defined as wind plus solar in the same parcel of land. This uses land more efficiently, as well as uses existing transmission infrastructure more efficiently by being able to share road infrastructure and transmission lines and substation. And it also leads to lower costs due to both of those things in addition, and as well as the operations and maintenance. And then finally, we modeled PV technologies separately. So fixed tilt is a form of PV that is exactly as it sounds. The tilt of the panel is fixed, it doesn't move, whereas a tracking PV, single axis tracking system, kind of tracks the movement of the sun over the course of the day. A fixed tilt system is more land efficient because of the lack of shading between rows. You can put the rows closer together. And actually, it turns out to be more cost effective in particular places. So by representing a fixed tilt PV system separately from tracking, we can better estimate the land sparing impacts of deploying fixed tilt versus tracking in certain parts of the US. Okay, so the next a little bit of detail I'll provide on the methods is the environmental and social impact scoring system that we used. So the first is we developed environmental siting levels. These we can consider as basically areas where we should not put any kind of renewable energy infrastructure because of sensitivities to particular ecosystems and habitats. So level one is essentially what is currently in practice. So this is siting as usual, legally protected is off limits. So level two is what we call administratively protected, meaning that this parcel of land has some kind of legal designation that would require consultation or trigger some kind of review. So it would be harder to develop in these areas because of that. And then level 3 are areas that we've deemed have high conservation value, but do not have any of those protections. And these, for example, important bird areas, TNC's identified ecologically core areas, and then they have this very extensive data set on resilient connected network that's important under various kinds of climate change scenarios. So again, these data sets have been compiled with a lot of consultation with TNC scientists, and these are the 3 levels that we were able to agree upon. For the national study, we took a slightly different approach. We took the data set that we gather in the West, expanded it to the Eastern, Midwestern, and Southern US, and then we categorized it into the following lists that you see on the right, and we scored them. So instead of a binary framework that we used in the Western study, where we said, no, you can't develop on this land under each more stringent scenario, we actually just said this, if you developed on here, you would be penalized given a particular unitless score. And so this is the map of what the environmental impact score looks like for solar PV. And this is what the social impact score looks like for solar PV. And for social impact, this is the first time we try to gather something like this for the US. So I will say it's not as well developed as the environmental one, but we considered productive farmland, scenic areas, recreational areas, areas that are very highly populated. And then we incentivize development on marginal farmland and in energy communities, which I'll define in more detail later, by giving them a negative score. And I want to say importantly that there is a companion report for Power of Place studies called Voices from the West, which TNC researchers interviewed Indigenous representatives and decided that the study would not include resource potential or cite any renewables or transmission lines through tribal lands out of respect for Indigenous sovereignty. But I do want to say that this does not include lands held sacred by Indigenous people that are not within the tribal territories, which is a publicly available data set. And that is because of the sensitivities of those areas. Okay, so before I go dive into the details of the results, I want to say that there was a very iterative process with respect to developing the scenarios. We had to run the scenarios basically in sequence. So we developed an unconstrained scenario where we could have development anywhere. So 0% impact avoided. And then we calculated that total impact and we ratcheted it down in 10% increments. So we then took down, basically said, okay, in the 10% avoided impact scenario, we can only have 90% of the impact in the unconstrained, and so on and so forth. So in the national results that you'll see this continuum that's based on this percentage, and that's because we didn't apply any binary exclusions in that study. Okay, in the interest of time, I'm not going to talk about power line. So let's go into the details of the results. So the land use requirements, the big headline is that we do need about up to 10% of available area. And by available area, that's like the area of the lower 48 states in the most pessimistic scenario. But in the best outcome, you only need about 3% of that. And so in the Western US, you can see that that ranges from half the area of New Mexico down to about a fourth. And then this electricity only is basically the 100% renewable only scenario, which is what we were identifying before. As you can see, that very much underestimates the scale of that renewable energy build out we'll need. In terms of the national requirements, this is a figure showing total land area and then the different types of energy technologies in their land use requirements. And you can see this gray bar, these gray bars indicate the land avoided in each of these scenarios. And then this percentage on the x-axis are those percent avoided scenarios. So the higher the percentage, the lower the social and environmental impact is. So as you can see, it ratchets the total amount of land decreases. And that 40% reduction scenario corresponds to that earlier map that I showed you, where solar is going to require the area of Indiana. And so we can do better than that by going to 60, 70, or 80%. We also see the shift from wind to solar as we conserve more land from development. So as you can see under siting level 1, there's a pretty equal proportion of wind to solar, and in the higher siting level, you see that wind percentage shrink, and you also see a larger contribution from rooftop and urban infill solar. Okay, so the next few slides show the actual build out. So I emphasized when I was describing the methods that it's really important to spatially locate where these power plants and transmission lines will be located in order to identify their impacts. And so we had to, in order to do that, produce these maps. So this is a map where all the blue areas are onshore wind, red is tracking PV, yellow is fixed. The light green that you don't see here is agrivoltaics, and then the dark green is co-location. So this is like the no unconstrained scenario. We don't consider any social and environmental criteria. And then this is the 70% impact avoided. As you can see, it leads to a very different build out nationally that where certain technologies will be located. You'll see that agrivoltaic starts to really show up in Washington and California, where it did not occur before. And you'll see a larger build out of fixed tilt and less wind in the Midwest. This is the equivalent map for the Western US. I'm not going to get into the details of this, but I want to highlight that we also looked at transmission corridors, and you can see that under an unconstrained scenario, there's more transmission requirements, and under a higher level of protection, we need less transmission because of the lower wind build out in the Midwest. Okay, so in the last step of the analysis was to do the impact assessment using those build out maps. So in this figure, what we did was we showed the total area of the technology. So here it's wind and solar in orange. And then on the bottom of the power lines, I'm going to focus mostly on the generation, which is the top set of bars. And then the rightmost bar is siting level 3, which is the most protective scenario. So what we find is that as we protect more land, natural lands from development, naturally that's going to decrease, but more development is going to occur on agricultural lands. And when we protect those high value, conservation value lands, we do see that it will significantly avoid development on those lands. So in the absence of those protections, we do see a very large amount of development in high conservation value areas. And then finally, with specific types of habitat, like for example, sage grouse, we do say that we can, in the highest level protection, we can avoid any development on sage grouse habitat, and we can significantly reduce development on intact, unfragmented landscapes. This is kind of an equivalent figure, but in a different, using bubbles for our national study. The main takeaway is that less than 2% of the land cover and habitat types need to be converted in the lower impact reduction scenario. So the smallest dot you see on the left, and this is on a log scale, is basically the amount of land that's impacted under our lowest impact scenario, our 70% scenario. Whereas compare that to the gray bubbles, which is our unconstrained siting as usual. So you can see for bat, grouse, tortoise, we can really drop that down to basic, almost zero. And then finally, we looked at a bunch of social considerations. In the Western case, we just looked at population and some demographic factors. So here I'm going to, because I know I'm running out of time, I'm just going to summarize that the more land use protections does result in fewer people hosting new wind projects. So on the x-axis, you'll see millions of people, and then on the, on the y-axis, and on the x-axis is the distance away from that power plant. So for the most part, for solar, it's about the same regardless of what siting level. But for wind, because of the reduction in wind, you'll see that fewer and fewer people are going to be host to wind farms. but it's very similar across the other technologies. And so what this means in aggregate is that by mid-century, we're going to expect that 10% of the population in the Western US could become a host for a new energy infrastructure project. So in the national study, what we wanted to do was identify who these people may be, what their demographics would look like. So in the national study, we looked at specifically energy communities, what percentage of all communities would be considered energy communities. And by energy communities, we are defining them according to the Inflation Reduction Act's definition, which is communities historically or currently hosting fossil fuel extraction, processing, and generation facilities, who may, of course, be at a large risk of losing a lot of jobs due to the energy transition. So under a lower impact scenario, we do see growth, and especially in the Southwest, a doubling of development, renewable energy development in these energy communities. And across all scenarios, we definitely see the same or greater. So there is a synergy between our lower environmental impact scenarios as well as our low social impact scenario. And then we also looked at prime farmland and croplands in general. So nationally, we tried to restrict development on highly productive croplands. We did not include agrivoltaics as part of that. So as you can see in the general cropland, we do see a reduction mostly coming from wind, a shrinkage of wind. And specifically in prime, highly productive farmlands, we also see a reduction of development under the lower impact scenario, and that's across all of the technologies. Okay, final set of results, the demographics of these host communities. So we find that it's going to be very heterogeneous across the US. This is a figure that shows the distribution of the percent living below poverty of all selected projects within the 70% scenario versus the 0%. So everything you see in blue is the low impact scenario, and everything you see in pink is the higher impact scenario. So as you can see, the agrivoltaics that shows up in California is all new under the low impact scenario. And the distribution of the communities is very large. So we start to see more development of agrivoltaics in more impoverished communities in California, and that is a deviation from the distribution for the rest of the US. And as another example, in North Carolina, you can see that under a low impact scenario, we see more development of PV projects in poorer communities versus the national average. And that's also true for California for tracking PV versus the national average. This is the same version of that figure, but now for percent minority. Again, North Carolina kind of stands out as having PV development, full solar development in low communities with higher percent minority versus the national average. And that's all true for tracking PV. And then finally, because a lot of this energy development is slated to bring in a lot of new jobs, up to 10 million new jobs in energy communities, we also looked at the percent unemployment in these selected projects. So as you can tell, just highlighting California, we bring more agrivoltaic development to communities that have higher percent unemployment under a lower impact scenario. Okay, so I'm going to wrap things up and then we can go to questions. If you have any questions, please just put them in the Q&A. So I'm just going to summarize. I know that was a lot of information. So the big takeaway is yes, good news. It is completely possible for the US to meet its ambitious climate goals while avoiding negative conservation impacts and directing benefits to certain communities. And trying to direct those to communities that need them. We find that high electrification has the lowest land impacts. I didn't talk about that in a lot of detail, but we could safely say that high electrification is compatible with low environmental impact. We see modest shifts from wind to solar, and especially solar in distributed, less land intensive types of solar projects. We do find that these land-sparing technologies like agrivoltaics, co-locating wind and solar can play a considerable role in avoiding these negative impacts. And it is absolutely important to consider the environmental constraints and social constraints up front, because in the absence of those protections and considerations, we do see negative impacts. We have some preliminary evidence to suggest that environmental and social criteria can be synergistic, though we will do a lot more to investigate that in the peer-reviewed paper. And then finally, we find that the demographics of these communities will be highly heterogeneous. So we need the state-specific, county-specific considerations and recommendations for ensuring that those specific communities benefit. Okay, I'm just going to wrap this up in just one last minute. So what does it mean to now think about revamping energy planning to address these wind, solar, and transmissions location-specific needs, impacts, and benefits? We really need to start moving from a project-by-project approach to planning, where we are integrating these social and environmental considerations more seamlessly into energy planning from the get-go and then on the downstream side as well. So there are lots of examples actually of this happening. I'm calling out just a couple of them here. So there's a least conflict siting plan that's happening right now in state of Washington. State of California has actually started to use the land use exclusions that we developed for the California specific study. The state of New York has actually implemented an Office of Renewable Energy siting. And then finally, I think like the holy grail is to try to actually integrate this much more seamlessly into our existing planning process. And I'm going to highlight this bottom bullet. So this is not currently being done, but I think is extremely important, is that we need to do integrated planning that's informed by bottom-up community vetting of these potential projects and determining the actual conditions for development. And there are two main reasons for this. It's that environmental and social cultural values cannot be integrated. There are just some that can't be integrated at large scale in a modeling study, mostly due to data availability, the need for site-specific surveys and or sensitivities around those those values. And for a project to really be determined as whether it is a net benefit or a burden to a community is really dependent on the project itself and the conditions for the development. So having the social license to operate, I think is going to be extremely important. And it's not something we can actually capture in a study like this. And so that bottom-up participatory approach is going to be critical for the success of renewable energy going forward. And with that, I'm going to conclude and have a very long list of thank yous to all my collaborators at TNC and funding support. And I'm happy to take any questions through the Q&A.
Great. Thank you so much, Grace. That was a really fascinating talk. I'm going to open it up to our moderated Q&A session. So again, you can use the Q&A button at the bottom of your screen to ask any questions that you might have. We've got our first question coming in here. It says, thank you for your presentation highlighting your research. How have you considered energy source trade-offs? Energy development exists to meet growing demand. When renewable development projects are questioned, doesn't that often lead to fossil fuel development instead, exacerbating the impacts of climate change and harming biodiversity globally?
Yeah, that's a really great question, and actually something that motivated this work is that I would say TNC is very much aware of this, that we're in a catch-22. The development, I would say no large infrastructure development does not have impacts. Yet if we did not pursue these low carbon infrastructure projects, we're going to have impacts globally. And so we're at this crossroad where we may need to make difficult trade-offs. And for some conservation groups, that means saying yes more yeses to more projects as opposed to their historic stance being no. So I fortunately am not in that position to say yes or no, but I do think that this is going to be an increasingly important concern. My role as a researcher is to identify the strategies that that reduce the intensity of those trade-offs. And we try to do that by highlighting and identifying the co-location agrivoltaic strategies that really bring win-win solutions, knowing that we need all hands on deck at this point. But thank you for that question.
Yeah, absolutely. Thank you for your answer to that. It's definitely a tricky situation. Okay, the next question says, thank you so much, Dr. Wu. I just want to ask about your experience communicating your work with policymakers and ask if you have any recommendations for academics who work in sustainable energy production, especially along the lines of ecological impacts of solar placement and development.
Yeah, I've been working on this topic for almost a decade now, and have evolved in my communication of this work. I will say that I've presented the results of these studies to decision makers, including people at the California Public Utilities Commission in California. And they are have on the whole been very receptive. I should caveat this with saying I have a very California-centric perspective on this. California has been extremely receptive to this because they already recognize the importance of community and conservation considerations in siting. And the journalists who cover these topics have really started to identify siting as being one of the biggest barriers to renewable energy development. So I do think that the thing that I've evolved to do more is to not point the finger at like energy developers. Like, we need energy developers. They're not the problem. I think we need to find common ground, and we need to come up with a process, the communication of this process, and coming up with like a way to bring us all together in a non-combative manner, because I think that that's how we initially started as a conservation community with energy planners and developers.
Yeah, absolutely. A somewhat related question. Someone's wondering if you can suggest scenarios for implementing that last recommendation that you gave, local bottom-up review and input on siting projects. They wonder if there are institutions that are currently supporting this.
Great question. In a presentation actually to the energy principals in California, I pitched this as an idea. Don't know how interested they were. I don't actually have any examples of this happening in the energy space. My closest example is in water planning. So the integrated water WIMP, I don't exactly know what it stands for, Integrated Resource Water Management Planning. So California doles out a certain amount of funding to municipalities and counties to help them plan water resource over the next, I think on like a 5 to 10 year basis. And so these local jurisdictions are responsible for coming up with a plan to ensure reliable water supply over the next however many years. I think we could set something like that up for energy. We should basically be able to take outputs of these larger scale models, potentially just even a California state specific model that says we need a certain amount of renewables by a certain amount of time. And this is what we project we need from your county. Where should it go? Can you tell us how we can meet this demand, from a community perspective, and what are kind of the conditions, the like procedural justice aspects of this development process that we need to have in place in order to do this? So I think there are existing analogs that we can draw from, but unfortunately nothing like this actually exists yet in the energy planning space, because we haven't actually needed to consider this amount of renewable energy build out in such a short period of time. That's locationally specific.
Right, you have maybe some good examples to draw from, but this is kind of new territory that you're working in here. Another question here, Marty Downs says, great talk, Grace. Do you have any sense about the characteristics of a community that are likely to make an energy project be seen as a benefit or a cost in that given community? Especially given that much depends on the exact project and community, etc.
Yeah, there are lots of existing studies looking at the social acceptance of renewable energy projects. A lot of it is actually on wind projects because wind projects have been around much longer than solar. What we have learned from wind projects is that procedural justice is as important as just economic benefits, pure economic, just benefits of, like the tax benefits that comes with a project. It's investment in that community. It's also because a renewable energy project needs to go somewhere in that community. It's not just the landowner that should benefit from that project, it's also the neighbors. And so it's the distributional aspect of the project. So there are a lot of considerations that the project developer really needs to take to factor in, but there are lots of studies that have done extensive interviews and surveys of successful projects and what community members need to feel like this is actually a net benefit to them, that I think would translate pretty well to solar. There is actually an ongoing study looking at social acceptance of solar. So we'll have a more definitive answer to that in the next year. But I think drawing on from prior experience with wind is a good way to start.
Yeah, that's really interesting. I have a highly related question. So you mentioned when you're building out this social impact score that that's so much newer sort of process and an environmental impact score, and that you're still maybe adding some variables and some considerations to that. So I'm curious what maybe some of the next steps might be with developing that social impact score. Are there other community attributes or things that you want to add to that to take into consideration in future studies? Or is that something you're going to get more information from these existing studies that you just mentioned?
I definitely think the ongoing studies, the one I'm in particular in my mind right now is this one that's being funded by the Department of Energy for being done by the Lawrence Berkeley National Lab. They interviewed communities around solar projects and also the project developers. So they're getting a better sense of what the values are of the landscape. Is it rural live, is it just the rural landscape that they're concerned about? So any kind of development is going to be an issue, or is it particular aspects? How can they make it more palatable? I think that the social scoring system is just inherently going to be a lot more complex and location specific. For example, like the viewshed issues, I don't think that our data set for that is not going to be particular as robust as it should be in every particular place. And then cultural values, especially, is something that we're missing. And I don't have a good idea for how to best approach that, given the sensitivity of certain kinds of cultural values.
Yeah, absolutely. It's a very complicated topic, and I'm sure we're all going to stay tuned and keep an eye out for your future research on this topic. We are at the hour, so I'm going to wrap it up here by thanking Dr. Grace Wu from UCSB for a fascinating talk and conversation. Grace, thank you so much for your presentation. That was so interesting. Know that there would be resounding applause if we were all together in one room right now. We thank you for taking the time to talk to us today. And for everyone online, thank you for joining us. This is the final talk of our 2023 NCEAS DEIJ seminar series. If you missed either of the previous seminars, you can find recordings of them on the NCEAS YouTube page, and this talk will be posted there as well. You can also find related videos and seminar recordings from previous years there as well. Thanks, everyone. Have a great week.